In this module, we will be looking at valence bond theory, which is another bonding theory we'll be using to understand how atoms in molecules are held together. So in valence bond theory, the principles that we build this on, one, and just a reminder of some things that we know along with this, the valence electrons of atoms reside in atomic orbitals. And these atomic orbitals can be the ones that we know well already. So S, P, D, or F. Or, as we will build up in this module, they could be hybrid combinations of these orbitals. And my cats really want to be in this video today, apparently. Okay, so if we take what we know here, we bring in a little bit of that quantum mechanics that we haven't talked about in a couple of modules. A chemical bond results from the constructive overlap of two half-filled orbitals. So if one orbital can hold two electrons, and you have two orbitals that are half-filled, when they overlap, if you get constructive interference, right, that's a building up of the wave function, that's a higher probability of finding the electrons there, and gives us two electrons for our bonding pair. Okay, and then one more. The geometry of overlapping orbitals determines the shape of the molecule. Now, the good news here is that valence bond theory is built on top of VSEPR. So essentially what we're going to do in valence bond theory is say, based on the VSEPR geometry and the information that I learned in the last module, I know that this molecule should be this shape. How can my orbitals combine and overlap with each other to make sure that I get this shape in the molecule? So for us, for now, there are two types of bonds that we need to worry about in these molecules. So the first is a sigma bond, and so that's what this lowercase Greek letter is. And a sigma bond is what you get when orbitals overlap end to end. Or another way to describe this is that they're overlapping head on, so they point at each other. If you have lobes that will do so, if you have an s orbital, it kind of points in every direction at the same time since it's a sphere. So s orbitals are really only going to be able to do sigma bonds. And all single bonds are sigma bonds. So if you only have one bond between two atoms, it will be a sigma bond. Okay, the next type, the second type that we have to worry about for now, is a pi bond. And pi bonds happen when orbitals overlap side by side. So we have to get some type of sideways overlap, and the only way for that to be possible is to use something like a p orbital. So for us, it'll be p orbitals only, but you can imagine that in a bigger molecule or something more complicated, p orbitals only for us, there we go, that you could do this with a d orbital because they have those lobes that you could bring together side by side. However, that usually happens when you get to things beyond triple bonds, which I told you we will not yet deal with. So we're going to be dealing with some more simple molecules. We're only going to need to use the s and p orbitals to make sigma and pi bonds. So pi bonds happen whenever you have anything beyond a single bond. So if you have a double bond, one of those is a sigma bond, right? The first original bond between the two atoms is a sigma bond, and the second bond is a pi bond. If you have a triple bond, one of them is a sigma still, and the other two are pi bonds. Okay, we're pretty much just dealing with covalent bonds here. So now when we talk about covalent bonds, we're kind of building up this definition that we've started with from in a much earlier module. And so now when we talk about them, we are talking about the constructive interference from overlapping orbitals, which are based in waves, which is how we're getting this constructive interference. And this happens for them on adjacent atoms. Okay, so if we look at H2 as an example here, some things that we know very well, each H has the electron configuration of 1s1. So I have this 1s orbital with one electron in it for each one. And if I were to draw a Lewis structure, which also approximates my Vesper geometry, since this is just a diatomic, it would look something like this. So these two atoms, if each one of them has an s orbital and they're next to each other, their s orbitals can overlap, and so we get this area of constructive interference if they overlap and have the same phase. So this is where the shading is going to be very important. It'll get even more important when we do molecular orbital theory, but it's important that if we want to show constructive interference, we show things overlapping with the same phase. So, because of this overlap, the probability of finding the electron is highest in the region of overlap, and what we find is that the negative charges, that are the electrons, are attracted to and stabilized by the nuclei in this area. Okay, so for H2, this picture works fantastically. So let's try BeH2. So we'll get up to a slightly bigger molecule, BeH2, and if we build a Lewis structure of this, BeH2 has 4 valence electrons, 2 from beryllium and 1 each from the hydrogens. If we draw a Lewis structure and Vesper geometry for this, it looks like this, making it a linear molecule. And the orbitals that we have available to us to make these single bonds between beryllium and hydrogen. Hydrogen still only has that 1s orbital. For beryllium, we have the 2s and we have the full set of 2p, right? And these are just the orbitals holding the valence electrons. We're only going to worry about the valence electrons in this model. All right, so when we make this picture, you can only use each orbital once, which just as a reminder, right? Because each one can only hold 2 electrons. So if it's in the process of sharing with another orbital to find a place to hold 2 electrons, we can't use it to overlap with anything else. So I have beryllium, and I'm going to start by using my 2s on beryllium, and it needs to overlap with hydrogen. And let's just, you can kind of put that hydrogen anywhere. I'm going to put it here. And mostly I'm going to put it there because I'm kind of planning ahead. I have to bring in a p orbital to make my next bond. So I'm going to want to use, because of where I've drawn this hydrogen, either the px or the pz, just so that my bonds are as far apart as they can get. Now I could have put my hydrogen somewhere else and used the py to make my other bond, but I just happened not to in this case. So I can draw these overlapping in phase with constructive interference. This is my sigma bond, right? It represents this line between beryllium and hydrogen. So for my next sigma bond, I have to use a p orbital because I used up my beryllium s orbital. And like I said, I need to put it as far apart from that other bond as possible. So let me put this p orbital here. Now, if I were just shading this orbital, right, I would need to shade one of these lobes. And then my bond with hydrogen, it could be with either side of the p orbital lobe, as long as they are in phase with each other when I do that overlap. So just for the sake of space, I'm going to put it on this side. So this constructive interference is my overlap that represents my sigma bond. But this doesn't look anything like the Lewis structure that I drew, right? And that's because this is very, very wrong. So I'm going to put a big ol' X through this. So this gives 90-degree bond angles. Like, the only way that the hydrogen overlapping with the beryllium s orbital can be out of the way with one overlapping with p orbital is to be 90 degrees away. Any other distance beyond that, and it's too close to the other lobe of the p orbital. And even if I were to try to do this with just p orbitals on beryllium and ignore the s orbital, which wouldn't happen, I would still have 90-degree bond angles, and I have no way to get away from it. But we know they should be 180 degrees. And so what valence bond theory will do is say, I know what my bond angles should be. How can I combine my orbitals to make that so? Also, if we do some experiments on BeH2, we can find out information about those bonds, and experimentally, both BeH bonds are identical. So they would have to be between that s orbital on hydrogen and the same type of orbital on beryllium. So the solution that we have for this is we are going to make and use hybrid orbitals on all, I'm going to underline all, non-hydrogen atoms to use for bonding. We will create hybrids by adding orbitals together to get what we need. And the way that we will know what we need is by looking at the steric number. And so this is the case where we will start looking at the steric numbers on every single atom. And I'm going to put this in giant red letters. I really mean all non-hydrogen. I really mean every atom for looking at the steric number. So you need to follow the instructions in these videos. Specifically, not any of the books. Your pictures should look like the pictures that I'm drawing. We will hybridize the orbitals on every single non-hydrogen atom. This is not what is done in the books, and it's very important that you follow these instructions and not the ones that are shown elsewhere.